Now there's another method, Milne Thompson method, by which we can easily find the analytic function for the given equation. Now there are the two cases. When mu is given, that is the real part is given, and when v is given, that means imaginary part is given. That means I part. When real part is given, then we use this format: psi1 z0 I psi2 z0. We can find psi1 by d mu over dx and psi2 d mu over dy, and we have to subtract them, and this is I also. Now this is the case 2. Take the screenshot, and when I am going to explain the questions, then you can easily compare that and understood easily. So please note it down, so that in order to understand in later how we'll apply these things in the questions. Now when the v, that is imaginary part, is given, we use psi1 z0 and I psi2 z0, where psi1 and psi2 is given as this. And after putting these values in the equation, we take exchange x with z, and y tends to 0. Now I'm going to explain this application on this equation. What that means, we have to find what is the most general analytic function if mu is given to us. Now here mu is given to us, that means case 1 is applied over here. So I am going to apply the case 1 over here. Now see, d mu over dx. Now mu is equals to x square minus y square. So psi1 is equal to d mu over dx. That means we differentiate with respect to x, so we get 2x. Now psi2 we differentiate with respect to y, so which is equals to minus 2y. Okay. Now I am substituting these values into this equation, that is integration of psi1, that is 2x z comma 0, and here I minus 2y z comma 0 plus c. Now I am replacing as x with z and y tends to 0. So we get over here 2z, and here plus, and this is 0, so it all becomes 0 plus c. Now when we integrate simply 2z, we get 2z square by 2, and simply we get z square plus c. So this is our analytical function. Now you can also check, apply this relationship along with this equation also. Now here it is given that now if the real part is given in this way, then we have to find the analytical function. We apply the same theorem over here, and from here if we find d mu over dx, so ex cos y. So when we differentiate with respect to x, we get ex cos y, and when we differentiate with respect to y, we get minus ex sin y. Okay. Now I am substituting these values in our equation when the real part is given. So we get integration of ex cos y z comma 0 minus I minus ex sin y z comma 0. Okay. So I am replacing x with z, and y with 0. So we get Ez cos 0 plus I Ez sin 0. Clear? Now value of cos 0 is 1 and sin 0 is 0. So ultimately this overall becomes 0, and we left with Ez, integration of Ez. Now when we integrate, we get simply answer Ez. So this method is very easy and very useful in order to find the analytic function.